The threat climate change poses is real and is happening now. Buildings and construction are hugely complicit, even more so than the automobile and livestock sectors. Buildings and constructions account for more than 1/4 of all greenhouse gas emissions through greenfield development, construction material production such as cement, and the burning of fossil fuels such as oil, gas and coal for construction purposes. Over the next 30 years, more than half of the expected building stock will be constructed, most of which will be in rapidly growing cities in developing countries in Asia and Africa. On average, 55 to 70% of the built area will be devoted to housing. Current national housing policies place emphasis on affordability, but little attention is placed on the environmental sustainability. This is despite 19% of the global energy consumption stemming from the residential sector. UN Habitat is advocating for a paradigm shift and recognising that improvements in the sustainability of the building materials and design of the household, as well as the introduction of environmentally friendly solutions for the operation and management of utilities. Such actions will have positive impacts in reducing embodied emissions from the housing and construction sector, as well as rendering the housing stock sustainable and more resilient to climate change. There are many methods that can be used to address embodied carbon. Here we present 5 such methodologies. These are in increasing order of effectiveness, coming from carbon reporting, comparison and design, carbon rating, carbon caps, and decarbonisation. Other methodologies have an indirect impact on embodied carbon. The table outlines the carbon reduction methods from the most basic to the most advanced, as evaluated based on their ability to reduce embodied carbon. The rankings of categories should be considered indicative, as within each approach, the implementation determines much of its efficiency. For example, a too pessimistic carbon cap will not challenge projects to implement in a meaningful manner. However, here it is considered a more effective measure than carbon rating, as it is mandatory to meet. This figure from Castro et al. Shows in green the estimated typical reductions for projects by applying each of the 5 different methods. In grey, we can see the additional estimated potential reduction for projects when each method is applied. We can see how different carbon reduction methods vary in their capability to reduce the embodied carbon of construction projects. For example, a reporting requirement does not actually require any improvement, even if some projects can make use of the information received and adjust design and procurement decisions. For clarity, decarbonisation does not yet reduce embodied carbon to zero, but applies to offset or export energy for balance. Each of the carbon reduction methods has its advantages and disadvantages. The main advantages and disadvantages of the considered methods are outlined in this table. Carbon footprint reporting is easy, so it builds knowledge and skills. That's one of its advantages. However, its disadvantages include that if reporting is only required, design and impacts will not improve. The second method, carbon comparison, is the most cost-effective way to influence. Options may be understood prior to acting. However, some disadvantages include comparison is not necessarily leading to best options being built. This may become a formality in some projects. The third method, carbon rating, has an incremental performance improvements providing additional incentives via better rating. However, disadvantages as also a poor rating is also allowed. The less ambitious projects may not improve at all. If we look at carbon capping, all projects must meet the stipulated threshold. However, setting the cap to a level where it is effective in carbon reduction and yet cost effective is hard to do. And the highest thing to try and do is to decarbonise. Advantage is that direct cost from higher carbon emissions is an incentive to reduce as far as possible. Disadvantages include that systems aiming to complete decarbonisation need a great deal of political will and suitable incentives to be widely applied. There are many different rating and assessment systems that include for embodied carbon. For example, these 24 systems are used in Northern Europe, which makes it the most active region in developing of green building systems on a per capita basis. Nordic countries are moving forward with regulatory development for embodied carbon, as is of some other countries. This region has enough experience to move to more efficient carbon reduction methods. Some of the regulations in this region have not yet entered into force, but you can see them coming in more and more. Policies and measures targeting embodied carbon need to target the early phase when possible, for example, before the planning permission. This is because low carbon design practices, especially when they target embodied carbon, are the most efficient and effective, as well as the most cost effective in the early phase of a project. By introducing this requirement early on, it is possible to encourage material awareness when designing structures and areas. The early phase of a project lock in the range of possible embodied carbon impacts for better or worse. There are still opportunities to reduce the impacts later on, but their overall impact tends to be more limited, and bigger changes would be less cost effective. When a carbon target has been set in the early phase of a project, it becomes a design target for the designers working on the project and sets the embodied carbon constraints the design team needs to achieve. As the project progresses, carbon and cost are known in more detail, but also start to get locked in. This is visualized in this graphic here. This diagram is structure of the life cycle stages as defined in EN 15978, which in turn define the reporting matrices. The circular form of a proposal to integrate a pre-design period at the start emphasizes the opportunities available to reduce the upfront carbon emissions associated with life cycle stages A1 to A5. That's the stages of production of the construction products and materials and delivery to site. You can see here in the diagram the hierarchy for embodied carbon reductions. So the first thing we should do is build less, effectively challenge the client brief for spatial efficiency, reuse and renovate existing buildings and infrastructure where possible, and carry out an audit of materials on site for circular economy purposes. So if we can't build less, then we have to build light. So we review the structural loadings utilised and spans, reduce the material quantities before relying on specification. Consider whole life cycle aspects, the replacement and maintenance. So make sure we design for durability, for long life, not that we have to replace things too early in the life cycle of an asset. Next will be to build wise. Know where your carbon is, include the big ticket items and repeatedly small ticket items. Explore standard modules, test design for manufacturing and assembly options, and material efficiency. So once we've gone through those three steps, the next step then, if we need to, step 4 would be to build low carbon. So to specify low carbon, renewable, bio-based, reuse or recycled materials from responsible sources. Be aware of uncertainty and variability in the data. And when we're building, we need to build not just for now, but also build for the future. So design for durability, flexibility and adaptability. Design for disassembly and circular economy of end of life. The last step is build collaboratively. So we need to measure, verify and disclose. We need to share knowledge with others so we can learn from best practice. A study by Hogsad and Bavarian looked at the economic impact of embodied carbon regulations in the European construction sector. Over 2 articles and publications identified these 6 interventions that can help reduce the embodied carbon emissions of buildings and pieces of infrastructure. So the first being make the best use of existing and future construction. Number 2 being optimize the design to minimize embodied carbon. Number 3, decarbonize the production of construction materials. Number 4, improve construction efficiency. Number 5, recycle and reuse materials and components. And number 6, prioritize materials with low or negative embodied carbon. So embodied carbon reductions of 41% could cut costs by 9% compared to the business as usual case. Each intervention emphasizes a different stage in the building's life cycle and involves different stakeholders in the construction materials value chain. The first, make the best use of existing and future construction, was added to provide a full overview of the mitigation options. However, the cost of interventions that seek to avoid or minimize new construction has not been analysed because they do not compare well with approaches to minimize embodied carbon of the construction of new buildings and infrastructure. The figure shows how the potential to reduce greenhouse gas declines at different project development stages. While many opportunities exist to reduce the embodied carbon footprint of new construction interventions, so from stage 2 to 6, efforts to minimize the need for new construction have the greatest impact per square metre, as you can see in the diagram. So, first thing, make the best use of existing and future infrastructure at the planning stage. So avoid construction by prioritising alternatives to build new. Reduce construction by optimising the utilisation rates of existing buildings. Also within the planning stage, renovate rather than replacing. Ensure an optimum utilisation rate for planned buildings. In the design stage, then optimise design to minimise embodied carbon. And next, during the construction stage, decarbonise the production of construction materials, enhance construction efficiency, recycle and reuse materials and components, prioritise materials with low or negative embodied carbon. And then during the project operation and maintenance phase, we need to operate our buildings and our infrastructure as efficient as possible and use renewable energy sources. So let's look at each of these steps in a little bit more detail. So the first step being make the best use of existing and future construction. Until construction practices have advanced such that the construction sector sequesters carbon in the built environment, regenerates ecosystems, restores biodiversity, and emits no waste, efforts to avoid and reduce construction should receive priority over minimising its impact. This can be achieved by avoiding vacancies and low use rates through strategies such as avoid construction by prioritising alternatives to new builds, reducing construction by optimising the utilisation rate of existing buildings, renovating rather than replacing, and ensuring an optimum utilisation rate for new buildings. So the second step will be to optimise design to minimise embodied carbon. Research has found that the embodied carbon of sports stadiums built between 2000 and 2011 range from 250 kilograms of carbon dioxide equivalent per seat, which is the London Olympic Stadium, to 3,500 kilograms of CO2 per seat, which is the Beijing Olympic Stadium. For pedestrian bridges, the differences are even larger, reaching a factor of over 10. These differences are mainly attributed to the volume of carbon-intensive materials used, since the materials' emission coefficients do not vary substantially by geography. Given those large differences, significant emissions could have been avoided if all stadia, pedestrian bridges and buildings were designed with minimum embodied carbon. The third intervention, decarbonise the production of construction materials, focuses on the heavy industries that produce construction materials. It seeks to reduce the carbon footprint of construction materials by changing production methods, switching fuels and improving energy efficiency. For example, the Swedish company H2 Green Steel is investing in hydrogen-based steel production. Using hydrogen from renewable energy sources, it aims to produce 5 million tonnes per year with a 95% reduction in carbon footprint. The fourth intervention, which is to enhance construction efficiency, focuses on improving the construction processes. Off-site and modular construction are typical methods. They involve completing part of the construction in the factory setting and assembling the final modules on site. This strategy abates the greenhouse gas emissions by reducing both material waste and transport movements. For example, a Dutch construction company, Ursum Modular Boham, has adopted modular and off-site construction techniques. The company reports that this approach enables it to reduce construction time by 50% and waste production to less than 1% of total materials used. This is in comparison to traditional construction methods where waste volumes can reach 10 to 15% of total material use. The fifth intervention, recycle, reuse materials and components, is to improve the building's end-of-life value and incorporate recycled materials and recover construction elements in new buildings and renovation. An example is the recycled cement is sold in the Netherlands as Freemat. According to a Dutch consultancy, this technology can reduce the embodied carbon in concrete by 68% while reducing cost by 56%. Because these recycling techniques can be deployed on site, they are cost effective. The sixth intervention solution is substituting conventional construction materials with alternatives with a low embodied carbon footprint, or that can sequester carbon dioxide, can help reduce the carbon footprint of construction. Bio-based construction materials, for example, often referred to in the European Parliament as wood-based construction, offer such sequestration potential. Most life cycle scenarios assign lower CO2 emissions to wood-based construction than to concrete or steel frame buildings. One requirement is that wood be sustainably produced, regrown and transported, preferably over short distances. This implies sourcing a substantial amount from within the EU itself. Forests and other wooded land cover more than 40% of the total land surface in the 39 European Environmental Agency countries, with forest cover and wood standing stock increasing. Case studies from Scotland find that timber can reduce a building's embodied carbon by up to 48% compared to the baseline case of reinforced concrete, and 58% compared to steel. A Canadian study that compared a cast-in-place concrete building and a mass timber structure found that the latter reduced embodied carbon by 24%. Now focus more on the reduction of embodied carbon by each material type. So start with concrete. So if we reduce cement content and use supplementary cementitious materials, we can use carbon. Specify low recycled and strong aggregates. Specify limestone, Portland limestone cement instead of Portland cement. Utilize appropriate mixes for each application. Specify high strength only when needed. Select from the lowest energy kiln type, for example drywood preheater and precalcinator if it's available. Utilize CO2 injection technology if applicable, like Carbon Cure in Ireland. In terms of steel, procure steel produced in electric arc furnaces. Avoid steel from basic oxygen furnaces. Avoid the use of hollow structural shapes in metal decking. Utilize bar only if needed. Utilize salvaged or reclaimed steel. Specify high recycled content like 90+%. For timber or wood, ways to reduce the embodied carbon is to utilize reclaimed wood where possible. Specify wood from certified sustainable managed forests, for example FSC certification. Specify fast-growing wood species. And specify wood products manufactured using electricity and/or renewable energy. In terms of insulation, what we can do to help reduce the embodied carbon is to minimize or avoid foam-based insulation products such as expanded polystyrene, extruded polystyrene, polycyclic structural insulator panels, and spray foam. Use blow-on insulation in cavity walls. Protect insulation from heat and water. Consider natural insulation alternatives such as wool, cork, denim, or hemp. Furthermore, reductions can be categorized by the building's elements. So if we start with the structure, the sub and the superstructure, we can compare the embodied carbon options for sub and superstructure at the early stage to identify an optimum solution. Typical base studies for the horizontal and vertical grid should be conducted at concept stage for different material arrangements to determine the impact on the total embodied carbon for each framing arrangement. A structural rationalization study should be conducted to determine the impact on overall material quantity versus efficiency in construction and fabrication. Reduce the weight of the structure where possible through voids. Maximize embodied carbon quantities should be specified for structural components. Targets can be achieved by cement replacements such as GHGs, low carbon concrete mix designs, low carbon materials, and using recycled or repurposed materials. Structural frames should be considered to have a dual purpose, i.e. the structure should serve as a shading device rather than introducing additional shading elements to control solar gain. Explore recycled sources of material. For the envelope, such as the facade and the roof, carry out embodied carbon comparisons on typical construction base during early design stages where decisions can be guided by benchmarks and data. Remember that it is in the hidden parts, for example the metal secondary framing of a build-up, that often contains the most embodied carbon. Where metals are used, limit their use and ensure that they can be removed and recycled at the end of life. For the mechanical, electrical and plumbing or the MEP, avoid over-provision of plant. A detailed load assessment must be undertaken. Typically, fewer and simpler systems will reduce the embodied carbon. Explore options for plant room locations which reduce duct runs. Design for deconstruction and recycling as MEP is typically replaced 2 or 3 times during the lifespan of a building. Specify refrigerants with low global warming potential, i.e. less than 150, and ensure refrigerant leakage is carefully considered in the whole life carbon analysis. Looking at finishes, furniture, fixtures and equipment, consider eliminating materials where not needed, e.g. by exposing surfaces. Utilize self-finishing internal surfaces like timber. Consider the cleaning and maintenance regime to be undertaken. Ensure the fit-out requirement is clearly understood to avoid finishes, furniture, fixtures and equipment to be replaced when the first tenant moved in. carefully compare products based on an EPD data, that's like the Environmental Product Declaration, recycled material, and also avoidance of harmful chemicals like fluorohides and VOCs. Consider the replacement cycle and specify for longevity. Choose products that do not rely on adhesives, so fabrics or finishes can be replaced. Be wary of trends that are likely to date and require early replacement. In terms of design for manufacture and disassembly, compare embodied carbon for design for manufacturing and assembly solutions with standard solutions. If DFMA is to be used, identify the elements by the end of REBA Stage 2. Examples include bathroom or WC pods, plant modules, facade elements, repeatable rooms, prefabrication structural elements including twin wall, columns and planks. Engage with the supply chain early on. Lightweight materials are preferable for transport purposes. Ensure that repeatable systems are designed for deconstruction. This is an example of Landsec's Sumner Street project of how design for manufacturing and assembly can reduce the embodied carbon. Two separate designs for the scheme were undertaken to REBA Stage 3 using independent design teams, one using traditional construction techniques and the other using Bryden Wood's platforms approach to design for manufacturing and assembly. An independent comparison of the embodied carbon between the two designs has identified a 19.4% reduction in embodied carbon intensity in the design for manufacturing and assembly design. Finally, solutions for reducing embodied carbon can be categorized by project stages. So first stage, the pre-design and site selection stage. So here we consider reuse in existing buildings before deciding to build new buildings. Assess soil type and determine options for the building's foundations. Some types of foundations are greater quantities of material than others. Consider salvaging or reusing materials from a building that is to be deconstructed. Set an embodied carbon budget for the project based on LCA calculations for similar buildings or case studies. In the second stage, the conceptual and scheme design, ensure structural systems are compact, efficient and not oversized. Design flexibility and efficient spaces that allow for long-term changes in use. Design for future disassembly and reuse. Consider the embodied carbon trade-offs related to architectural design decisions such as massing, envelope systems, foundations and landscaping. Conduct a whole life cycle analysis of building or perform life cycle analysis for hotspots materials or assemblies with higher carbon intensities. Select building systems and assemblies that minimize embodied carbon. Assess availability of local reused or local source materials. So you can see here on the diagram the different actors or stakeholders involved and how they can, and which ones that I just spoke about are more that I can have most influence on. Moving to the design, development and construction documents. Specify material characteristics that result in low embodied carbon. Substitute like for like materials that offer lower global warming potential. Consider the embodied carbon trade-offs related to architectural and structural refinements and changes. Update your life cycle analysis for the whole building as needed. Stage 4, the bidding and procurement. Incorporate clear embodied carbon goals in all procurement language and set building systems on material specific goals. Include requirements for product substitutions and specifications. Request embodied carbon data, including EPDs from all vendors. Include previous work, experience, and propose solutions that address embodied carbon in any procurement selection criteria. Design a subcontractor selection process that incentivize bidders to offer lower embodied carbon materials and methods. For the construction project stage, establish clear guidance and targets to reduce construction waste. Hold contractors accountable for delivering low embodied carbon design committed in the previous phases. Consider offering monetary performance bonuses for additional embodied carbon reductions identified and executed during the construction process. Document the as-built embodied carbon content of the building and publish the data. Update the whole building life cycle analysis as needed. For the sixth stage, the occupancy stage, where the maintenance, renovations and tenant fit-outs are considered. Debrief and apply lessons learned to future projects. Establish embodied carbon reduction targets for future renovations and tenant fit-outs. This table shows how various stakeholders can help in decarbonising the construction sector using different strategies. So the main influence here being policymakers, owners, design professionals and the contractor, and the strategies ranging from reusing buildings, reusing materials, focusing on the whole life cycle carbon analysis, using less Portland cement, right-sizing the project, using bio-based and other carbon storage materials, optimizing use of materials, and sourcing from lower global warming potential manufacturers. Currently in Europe, it's mandatory to assess the energy efficiency of the operation of our buildings and associated carbon. However, the regulations have currently been updated, and in the near future, they will also include the embodied carbon parts of it. Whether the two are separate or not, the overarching theme of regulatory development is eventually to be able to handle embodied carbon as a regulatory aspect in the same way as the energy efficiency ratings are, for example, under European and other regulations, with highly standardised calculation methods and cost-effective and robust processes. In some European countries already, such as the Netherlands, Denmark and so on, already require whole life cycle carbon to be carried out, which includes for embodied carbon. This is common in other countries such as Ireland, where the Climate Action Plan has committed to having whole life cycle carbon included by the end of 2025. So therefore, our current energy performance certificates, or the building energy rating, will get replaced or updated to include also the embodied carbon associated with our buildings. Similar to the operation of our buildings, we need to not just assess the operational carbon and associated greenhouse gas emissions, but also have to set minimum standards. So in the embodied carbon target alignment, in this figure shows the range of performances based on benchmark projects and the need to improve the average, which is on the left, and the proposed rating badge, which is on the right. Current best practice performance is considered to be a C rating, while a B and above is considered a robust stretch target. Though only 4 typology rating bands are provided currently, the methodology can be repeated for other typologies or scope of work as more data becomes available. The bandings do not currently differentiate between new builds and refurbishment, and this banding here is from Letty. For more information, you can use the useful links here in this table.